right. So why are we doing all this again? We need a target distribution, right? We're going through all these steps to get to our target distribution. So now we need to think about what's going on, right? We've got theta, which is multivariate normal, and E, which is multivariate normal. So the first question we have to ask ourselves is this: what distribution do they add to give us what we think the data should be? A normal plus a normal. It's a pretty easy one to add. It's still normal. Okay? So it turns out we have a distribution that's normally distributed. In fact, the conditional distribution of the data given theta is normally distributed, right? So I'm a slide to it. What I just said about adding them together is coming in just a moment. But if you think about what we're doing, right? Y is normally distributed. This is the data. The mean vector, remember the normal distribution has a mean vector and a covariance matrix. The mean vector for y conditional on theta is given by that very first part of this equation. Sometimes in generalized linear models, we call this the linear predictor. Right? It's a multivariate model, so that means there's more than one prediction going on. There's one prediction per item. The covariance matrix, now again, this is interesting because this is conditional on the latent variables. Right? Once you condition on the latent variables, the covariance matrix of the latent variables kind of goes away. They're given to you, right? We need it for the next step, but we don't have it here. So now what we're saying is once we know the latent variables, then our distribution's covariance matrix would take that of error. And the way that we see that, so we flip back a slide, if you think about expected values effectively, right, what we're looking at, variances, if theta is not random, if it's conditional on, right, so we know it's conditional upon theta, then all of this right here is a constant right there. So when we look at the variance or covariance of our data, it's given solely by error. It's the part where we want to go and do something with theta where that becomes an issue. How are we doing with all that? All right. But that's not our data, right? Our data, remember our target distribution, we're trying to compare our model to our data. This is our model. It's conditional on theta. That's our model. What is the distribution of the data implied by our model? Because once we see what our distribution is implied by the model, we can think of what the target should be. Right? So, quick notes about types of distributions. If you have two random variables, x and z, the conditional distribution is often written f of x conditioned on z. Cool? Cool. Conditional distribution is also equal to the joint distribution, x and z, conditioned on z, marginal, divided by the marginal. So you can always look at conditional distributions this way, or joint distributions here. This also would be the case for our theta and the variable, although this slide's a little bit of diversion. I started to take a different track with this. I left this in because actually this is how you can derive factor scores, the distribution of it. I think we talked about it last class. I think I had an equation of the factor score somewhere in the last class. It comes from multivariate normal distributions and marginal or conditional versions of multivariate normal. So this is a segue you probably don't need. But the key here, though, use that to get to the joint distribution. The key is what we need to do is integrate out the joint distribution. Now it's time for the wave. Sorry. So a marginal distribution is the distribution we're after once we remove the influence of the latent variables. Turns out this thing's super important in what we do. In fact, next week's class is about difficulties, the hard reality of multidimensionality, and part of that's estimation. It turns out we need this distribution to do a lot of maximum likelihood estimation as well. So we estimate it joint with the latent variables, we have a problem. We need the marginal distribution. How are we doing? Yes.
Just a quick question. So here you have the function of yp.
Yep.
Like in the previous slide, you have the function of theta p. at the end.
This right here.
Is that the same?
So think of it this way. If x, what I'm calling y, and z was what I was calling theta, right? To look for the marginal distribution of it, to look for the joint distribution, excuse me, of y and theta, I need to multiply the conditional distribution of y given theta by the marginal distribution of theta itself.
That sounds like Bayes.
Actually, I'm glad you said that, because you can get to Bayes' theorem from this also. Right? Bayes is the flip. Right? But here, this right here, we'd call a prior distribution of theta in Bayes. But in this case, if you just have two random variables, it's just this distribution. That's all. So I don't know if I answered your question though.
More or less, yes. So in terms of notation, that's my specific question, because there you have theta, but in the next slide you have y,
Yes.
t. So that's the same thing.
Yeah.
Okay.
No, pardon me. This right here,
Yes, exactly.
that is not the same thing. That is what we need.
Okay.
That is where we're going. This right here is the distribution of the data that is implied by our model. Right? Once we get rid of the things that don't exist. So that's how we read this slide, right? We need what y is once we go and look at the joint distribution of y and our latent variable. Now I could have shortened this notation. I could have just plugged in this into that equation, but I didn't, in part because when you see this right-hand side, I often think what Nathan thinks, looks like a prior distribution. And this applies beyond priors. It doesn't have to have a prior to make this happen. We still need to have the marginal distribution of the data implied by the model.
Thank you.
You're welcome. Yes, Sergio.
When you're writing the integral that way, what are the limits?
Haha. The limits is the space of theta. So what we're doing here, if you think about it, this is a joint distribution. We have all the y's and we have the things that actually don't exist as theta, right? Theta itself, this is actually a multidimensional integral. It's our shortcut. This is supposed to be a vector here. Theta, we have to go back and think what its distribution is. And so because the theta's distribution is multivariate normal, we know in each dimension the limits of the theta distribution are the limits of the integral here. We have to go across the entire, integrate across the entire sample space of that distribution for this to hold. Does that help?
So in this case, across each of them, it would just be negative infinity to infinity.
That's it. The real number line for everything. Real times 4 or whatever. Yeah, that's it. So I'm trying to give you like the backstory too. So here's the funny thing. When we get to diagnostic models, theta isn't normal anymore.
Correct.
In fact, it's not even continuous. So this no longer is an integral, it's a sum. And what we sum over is the number of classes that we have. The same thing in latent class models as well. The other funny thing about that, though, is this is also the core of the marginal maximum likelihood estimator itself. Right? When we get next week, if I build the slides the way I hope to, we'll talk a little bit about marginal maximum likelihood, because we have to do this to estimate all the parameters of the model. And that's what slows us down when we're not in normal land. Okay? But today, right now, we're in normal land. So it turns out this integral, which looks terrible, and believe me, it's even more terrible when you code it, turns out with multivariate normal distribution, there's a nice property that allows us to not have to do it. We can just use a formula. And that's what I had mentioned a couple slides ago that I said it's not for this slide, that's later on. But if x is distributed normally distribution, if x is distributed normally, multivariate normally, then both conditional and marginal distributions of x are also multivariate normal, right? So that means we can show that f of y is the data should be multivariate normal. So when we use a CFA model, we are assuming or implying the data follow a multivariate normal distribution. Now, the parameter vectors that go here, that comes next. How about, who wants to do some mathematical statistics? Let's keep going down the rabbit hole. Huh? Yes? How about some expected values, but with matrices? Let's see. Let's work on the mean. The mean is the expected value, All right, so remember the expected value, vaguely? From a statistical point of view, anybody want to tell me the expected value of y is the integral across the space of y times f of y dy. Did I get that all right? There's too many y's there, but anyway, yeah, whatever. The function of y. Basically, it's this, right? We take each numeric value, we weight it by its likelihood, and we integrate across the space. That's expected value. You can show that expected values, they'll behave in really regular ways. How many of you have done the math stat classes? Some of you have. That's, I think, what half of math stat is in the beginning, is figuring out how expectations work in many ways. But think of it this way. I'm going to use less technical language than that. But what I'm showing you has that solution. If you're all into the math stat, go ahead and show me that I'm wrong, or show me that I'm right. Prove it. But here, the expectation of y. We need to know that's the mean of the marginal distribution of y. Basically, what we expect the mean of our items to be, the vector of it. Well, we can substitute y with its model equation, right? So here, y is just this matrix form right here. And then turns out, there's a whole algebra of expectations in mathematical statistics, so you can do some shortcuts to get expectations work. We can actually distribute this expectation across the sum. Since we have a sum here, we can distribute it. So mu turns out to be a constant. So the expected value of a constant is just that constant. So it becomes mu. Poof. Lambda in this case is also a constant, but theta has a distribution. So the expected value of theta is the mean of its distribution. And then the expected value of the product of a constant times that is the product of the constant times the mean of that. That's what this is right here. And then finally, we have the expected value of error, which is error has a distribution, therefore it's set to 0. So what we've just shown is that here, the expected value in the general condition is the item intercepts plus the factor pattern matrix times the mean vector of theta. Now, what did I just say usually happens for the mean vector of theta?
0.
It's 0. So usually this just becomes mu. Or in other words, when you look at your item intercept in the CFA model, it should align with what the item mean is. All right? Now you're getting my thought about target distributions. Right? I see a little bit of a smile. Maybe that's because I'm really funny, or maybe because it's like that's where it comes from, right? But that's part of it. How are we doing? Any questions on that process? Yeah.
The error of theta is mu?
The expected value of theta, meaning the mean of theta. That's what expectation really means, mean. What do you expect it to be?
Yeah.
But in a theoretical sense, like an infinite sense, right? And because we defined theta as multivariate normal, and we specifically defined its mean vector, that's what this expectation of theta becomes right there. It just becomes its mean. Okay, that help? All right, are you still sort of with me? Ballpark it. Like if this doesn't make sense to you, don't worry about it. I'm not going to go and quiz you on this. Like I did not expect you to do matrix algebra in this class, but I'm going to make you do it. I just didn't expect it. Yeah.
Is this related to the linearity of expectations too? It's like expectation.
Nah. That's another tangent we don't need to go.
Okay.
All right, who's got a seatbelt? Because now it's time to buckle up. And Nathan, this will apply to you because we talked about this recently. What is the covariance matrix of Y? All right, let's do the same thing, shall we? I substituted the model in here. I forgot error on this first one. I need to make a note. Slide 16. Error should be here, in here, right? Because error shows up there. So that first term should have error. So the variance is an interesting expectation. The variance, let me just be consistent with my notation here. Variance of y is actually equal to the expectation of y minus y bar squared. Right? And so to do expectation, then that means you can use this formula up here, but just substitute y minus y bar squared into that formula, and you get its variance. Okay? It's a little bit weird, not super important. Just follow what I'm about to do here, right? So if error should be in the pink, I can actually go and take these quantities and start parsing them out. I can try to do, you can almost distribute variance, but not quite. Because think of it this way. If you have more than one random variable that you're taking a variance of, right? Like the variance of like x plus y. Like say z is variance of x plus, variance of x, say you're creating a new variable z and it's x plus y, right? The variance of z is the variance of x plus the variance of y plus 2 times their covariance, right? So it's not entirely the case that you can distribute variance unless you can show that x and y are independent, right? If they're independent, then you can distribute it because the covariance is 0 under independence and multivariate normals. So then that part, the 2 times the covariance, just becomes 2 times 0 and it goes away. Okay? So, also, the variance of a constant. So first of all, anything with a constant is uncorrelated because the constant is a constant, right? So mu's out of here. That's my gone. There's no variance of mu here. Mu just does not contribute. And you can think about it this way. If I have a random normal variable between, say, standard normal, generate it, and I add 10 to everything, guess what? Its variance is still 1. It doesn't change, right? I just moved the location, but not the variance. So now we're left with lambda times theta plus e, which doesn't show up here. It turns out theta and e are both random variables, but by definition of our model, I didn't put it in the slide, e and theta are uncorrelated. Error and theta are uncorrelated. So that means now we can separate out these two without the covariance. How we doing? Everybody in the back, front? Even though I'm farther from you in the back, I'm still looking, all right? So if you have questions in the back, let me know, all right? In the front if you have questions, but you in the middle. No, I'm just kidding. So here's the fun part. This term, this first term, theta, right here, that lambda is technically a constant, but it's a matrix, a matrix of constants. So really what happens is we have to look at the random variable first and think about its covariance matrix. And we defined it to be this letter phi, capital Phi. So when we multiply theta by a constant, what happens to the variance is what we call a quadratic form sometimes, right? We have to pre and post multiply it by that constant. And in this case, to make the math work, it's lambda times lambda transpose on the other side of that. So that is where you see this form start to show up. Lambda phi lambda transpose. Finally, the variance of error, we already defined that to be this psi matrix. So it just stays as itself. But now we've just derived what this distribution should be, right? And I'll take the usual case. When mu is 0, our data should look like this. Our model implies the mean of our data should be mu. The covariance matrix of our data should be lambda phi lambda transpose plus psi. Right? That is our derivation of what our data should look like when our model fit. That gives us a hint as to what the target distribution should be. How are we doing? Yeah, Cass.
Is this assuming continuous, or is this like getting all?
Yeah, we have to make that assumption it's continuous. We conveniently forget it in a lot of practice of CFA. But yes. Shouting, yes.
The transpose of the constant should be the formula connect to the dimension.
Oh, you know what? I think you're right. Yeah, it should be lambda transpose. Here I have number of dimensions by, actually no, it's items by dimensions, right? Pardon me. No. Let's see here. What do I define lambda as? Lambda, yeah, this should be items by dimensions. So I had flipped that. So this, if lambda is number of items by number of dimensions, phi is number of dimensions by number of dimensions, right? So these two will make a product. Items by dimensions times dimensions by dimensions are multipliable. Then the last one needs to be transposed because that is now the transpose of its dimensions by items. And so the result of this is an item by item matrix. Does that make sense? Did I answer that question right, or am I missing something?
No, just me missing the definition for the lambda. It should be I times D, but I written the third as the D times I.
Yeah, I'm sorry for that typo. I accept all fault. I apologize. Other questions? I see.
Stan berated me enough to figuring that in my head.
Yeah, that's the thing about matrix algebra. It won't work if the dimensions don't match. The pre-multiplying matrix, the number of columns has to match the number of rows of the post-multiplying matrix. Right. And all the computers will tell you dimension mismatch or something along those lines. Okay. So this brings up a hypothetical. This is what we would call H0, right? We have a Q matrix that defines this. And I just said before, the Q matrix is our null model. So those of you who took CFA and you saw the H0 log likelihood, you can find that from this distribution right here. You plug in your model parameters, go to the multivariate normal likelihood, plug in your data. Right? Multivariate normal has a place for data and parameters right here. If you do all of that, you'll get the log likelihood of H0 if you fit an M plus or Levon. Remember that at the top of the output, H0 log likelihood usually shows up? That's where it is, right there. Yeah.
So this is, so if H0 is the, it's unstructured, everything gets estimated in there.
Nope.
Oh, well,
H0 is our model.
yeah.
I haven't gotten that farther yet.
Okay.
So we're going to stay here at H0.
Okay.
That's our model implied. But I'm going to take your if, I'm going to turn it back on you. So what do we compare this against for an alternative?
Less parameters.
Back that up. Just a second. H0, remember, when we do a likelihood ratio test, right, the null model has to be nested within the alternative model. Right? And that's a clue for what our target should be. What model subsumes this? Or another way of putting it, in what type of model could you come up with such that this result is nested within it? How about I start making some hints? Do we need the same distribution? Yeah, we need it to be normal.
Just a sample distribution.
Hold on just a second here. We're getting close. Yeah, I would say yes, but it's still a model. So mu, that's saturated. That's a mean, right? So that not much there. But the covariance matrix, that's where a lot of the magic happens. We have to think of a covariance matrix that subsumes this. Well, it turns out the covariance matrix where we just estimate every element uniquely without a model is what we do. And that turns out to be, as Alfonso mentioned, I think Nathan used it before, and Vladimir, you talked about the sample. Sometimes we conflate that with the sample, but it really is our maximum likelihood estimates of our sample main vector and our sample covariance matrix. Right here. Right? So our maximum likelihood estimates of it are like, I'm using ML for this framework because it, remember, there's a difference in variance between ML and what we often call the sample variance. Although it's a little weird. The ML estimate variance is biased. You heard about that way back in basic stat. So that's why in the denominator variance, in the denominator of standard deviation, you have an n minus 1 or n minus number of parameters if you're like in linear models and you're looking at residual variance and so forth, right? Or n minus number of parameters minus 1. You know what I'm saying?
Rebel.
Yeah, not here.
Okay.
Yeah. Sorry, like,
Oh yeah.
nip the conversation where I have to. This thing right here is just estimated. It's just your ML. It's like taking an n and putting it at the bottom of your denominator for all your variances and your covariances as well. So literally, here, if we had 10 items, we'd have 10 means to estimate. We'd have 10 variances to estimate. Now here's the quick one. Let's then choose 2. 45. I think it's 45. You can check me on that. 45 covariances to estimate. Right? Turns out this general model, and I hesitate to use the word sample because I oftentimes in basic stat we use sample for those unbiased estimates of things. But here, our model, or all of our CFA models, are nested within this. Because a CFA model is multivariate normal, and it fits exactly when sigma is equal to this form right here. Thought you were excited. Yes! That's the one piece of information I needed. I'm just teasing. So, why is that important? I know Lisa's doing the countdown thing. I don't have time for that. I just talk about something stupid like this. Countdowns. Now the countdown's over. Why is this important?
We can see how well our structure matches the
That's right.
unstructured.
We have a known form, a known target for what our distribution should be. If our distribution is close to what the data, or this saturated or alternative model appear to be, we can claim that our data don't misfit the data. Think of the terms of hypothesis. You can never accept a null hypothesis. And model fit is sort of making you do that, right? We cannot reject the fit of our data, but that's where it starts. But let's dig a little bit deeper, shall we? Let's look at the mean. The mean vector from the data, from the saturated, H1, is mu1. And from our CFA model, it's mu plus this thing, right here. Turns out, so long as you freely estimate mu, it's going to match, or this term, and let's go with mu equals 0, although it's not needed to show this. But basically, whenever you add a term to what some term should be in this model sense, it's going to fit perfectly. Because these are free parameters that you're estimating. And if there's a gap between what's in the data and what your other parameters are, they'll get filled in by the thing that's being added to it. Right? So if we didn't entirely describe it with this side, or if mu is 0, turns out we have a bunch of free parameters to soak up the difference. It fits perfectly. So in most applications of CFA, model fit to the mean is not needed. What's the ramification for that? In fact, in most models it's like this, although not entirely. The mean of an item won't tell us whether or not we fit the item well or not. Right? Whether or not we can recover the mean, almost all models will. This is another problem I have with the RMSEA they use in DCMs. It's just a freaking mean. And the number of decimal places that are out there. Yeah, you're talking about rounding error. Anyway, sorry. It's papers I don't have time to write, but this would be a great one. Hey, quit doing that. All right, let's look at the covariance matrix now, shall we? Model implied is this. Saturated is sigma 1. And if you look at the diagonal, where the variances lie, it's hard to see with this matrix form, but I wrote it out for one item here, right here. But the diagonal of it has a term that's loadings times factor covariances times loadings transpose plus residual variances, or unique variances. So yet again, we're in a situation where if this first term right here doesn't fully incorporate the variance that shows up in the data, our model is not going to have a problem with that because we're just going to estimate a variance that fills in the difference, right? So long as, of course, the variance stays positive. That's usually not a problem. I guess historically in factor analysis, there are negative variances, unique variances. Have you heard that term before? You know what they're called? Psychometric trivia? Haywood cases. You may have heard that in exploratory factor analysis. But that doesn't happen in most cases. So what that implies this, that for most applications, so long as we're not doing something to put constraints on our residual or unique variances, then the diagonal of our covariance matrix will fit the data perfectly as well, or near perfect, within rounding error, usually. So, looking at inspection, model fit gets determined by how well the off-diagonal elements in sigma 1 match the off-diagonal elements from lambda phi lambda transpose plus. How's that? So when we talk about the focus of, Nathan, you mentioned it and I sort of shut it down, but I'm bringing it back now. The residual covariance matrix, right? We could form a residual covariance matrix by taking sigma 1 and subtracting off this, our term. That's what's left over. And we're going to figure out, once you do that, if you do it with estimates, you'll pretty much always see the diagonal of the residuals is 0. It's the off diagonal that matters. But this forms the basis for most model fit. So what we're saying here is the following. If we believe our data follow a CFA model, we need to establish that our CFA model is not different from what we would see in the real world if we didn't even know that was the case. Right? If we just collected data and estimated the covariance matrix, our CFA model should fit that form. Right? Not by chance, by design. How often does that happen? Did Lisa give you projects in her class? Or no, not for factor analysis, right?
Yeah.
She did.
Yes.
Did you have good fit for your data in your projects? Really?
Acceptable.
There was a.
Okay. I was gonna say it rarely. It's hard to do right off the bat. But that's where. So I hope this has been helpful trying to figure out what we're doing is we have a model, right? Everybody needs to do CFA. How do we determine it fits? Well, first of all, we have to ask, what's the model imply about our data? Here we saw it was multivariate normal, and it has this really complicated set of covariances, matrix products for covariances, right? But that leads us to say, yeah, but what would that look like if we didn't have our model? Like, what's the most general form of multivariate normal? It's where we estimate everything. And so every CFA model falls under that. Yeah.
What if my marginal doesn't follow?
Oh, you're
So
screwed.
you have like 2 sources, right?
What if? It always doesn't follow a normal, because normally we apply this to liquid data that's categorical. Yeah.
Would you have the specification of that part as the model part?
Yeah, there'll be all sorts of problems. Let's put it that way. Model fit is probably the least the problem there. Like, it's just not going to fit. You're like, but I will say this: the reason why we do CFA still, I'm almost convinced, is because even though this took a little bit of getting to, like, it's a single equation. We can see it. We can work with it. But right, Alfonso, most data don't fall under most data that CFA get applied to, at least in our social science world, aren't continuous at all, right? They're just categorical items, effectively. And yeah, you can talk about, there's a whole literature on like how many items are enough and what do they need to look like. It boils down to how well does a normal approximate the marginal distribution of the item. And so what does the marginal distribution of the item need to look like? Well, let's look at the moments of the normal. It needs to be single peaked. You can't have a group of people on one side or the other. It needs to be unskewed, so a big pile of people in the middle, not on the tails. It needs to not be overly kurtotic, right? So roughly the same size it needs to be. And if you have that, sure enough, the model is decent. Normal is a decent approximation. I've never seen that in any data I've actually played with. Any thoughts, questions? Is this filling in gaps, or is this something you knew already? You hadn't seen this before. Filling in gaps? Has it been useful, or is it like, get to the point?
My question: if we can estimate an unstructured covariance matrix, why do we want and if that fits the data?
What's the story then?
Well, yeah.
Right? Okay, so I've got 10 items. I'm trying to measure your neuroticism. I'll do another big fun. Not that you're neurotic, but let's imagine I'm a bit neurotic. Imagine okay, forget. I'm measuring your openness to experience. Let's do that. That's just nice and variable. All right? If I'm doing that and I see, oh, I can estimate the covariance, here's 10 items, and you give me that, and I'm like, oh, look, here's your covariance matrix.
Yeah.
What's that tell me about you? Not a whole lot.
No.
Right? What I want to do is figure out, basically map what your responses are onto the continuum. So it's a measurement purpose in general. is either responses representing your belief, although we know that responses are filtered through response styles and other things. But that's sort of it. We want to take your beliefs or behaviors and put them onto a continuum. And that's what's so important to establish the CFA model. Because the CFA model is that continuum. So we often don't use it for that purpose. We use it for other things, like how many dimensions are there, or what model fits better. But that's a good question. Yeah, Vladimir.
All of the things that we have discussed here, so are they depending on the estimation method? For example, here, I would say that we are using something like full information method.
Okay, we're about to talk estimation next week. So hold on to the full information for just a second. Right now, I'm trying to give you the conceptual definition. Okay. The one catch, none of this is dependent on estimation with the exception of this. I did not specify, to do some of this algebra here, I did not specify prior distributions on some of the parameters. And as we know, if we go into a Bayesian framework, we may have to put priors on those. So I would say this, right now what I've done is agnostic for estimation with the exception of using uniform priors and Bayes for some of these to show this. If I didn't have that, this derivation gets more complicated because now those priors may have things that are no longer independent or otherwise there. Does that help?
Yes.
Thank you. Cass.
When we deal with categorical, should we expect to work with a function of the item, the function of YPC, of like the category?
I love that you asked this question because this is exactly what I was about to ask everybody. No. Yeah, yes, we will need a function of it. Yes. Yes. But try to mirror what I just did with categorical is the thing I'm going to challenge you to think.
Yeah, that's nice.
So, okay, what is the multivariate distribution we're after? What does it look like? How do we describe it? Those are the questions you ask to go from one item to the multivariate set to look at. And that's actually where we get into the paper that I sent this week, which was impenetrable in many ways. But at the same time, it was like it's like argon, right? Like this is the psychometric equivalent of the bottom end of the dating pool, right? You just got to give these people a chance. I'm just kidding. I don't know if that's a good way of putting it, but anyway. All right, leave the dating analogies aside. It's like the end of the fruit at the grocery store. When everybody's picked over the bananas and you really want a banana and there's like one that's sort of green or maybe brown or maybe bruised, you're like, I can cut the bruise off. That's what I mean with it. Is that better? That's better. All right. Other questions? Okay. So, absolute model fit can be assessed globally, right? So now we have two models, right? We have this one, where the saturated version comes from, and we have this one, where our model comes from. A global model fit would be an overall comparison between the two. We talked about likelihood ratio before and so forth. But that global is usually one statistic overall. Then we can also talk about local misfit. Remember we talked about where misfit shows up is in the off diagonal of the covariance matrix? Right? That local misfit can start to talk about if a pair of items don't fit what the data look like. Right? And there are all sorts of ways of that. One of those is the residual covariance matrix I just talked about if you look at each element. And there's also different flavors of residuals. There's normalized, there's studentized, which is normalized usually, standardized, raw residuals, all that stuff. Furthermore, the methods vary by estimation. Now this is where the estimation starts to throw a difference. Right? In ML-based work, likelihood ratio tests are used quite a bit. And not only that, we can derive what we need to understand what the distribution of residuals should be. And a lot of this is because even though this looks complicated, there's no integral involved in it, whereas in other models that integral won't go away. So it's somewhat tractable, although not for me. Other people will have to figure that out, right? So if you're using ML for CFA, you'll get a big list of these like model fit indices. Right? If you flip to Bayesian, good luck. But the philosophy is still there, right? And later in the slides, I have a link to a paper that Jihong, many of you know Jihong, former grad student. By the way, Jihong is starting as assistant professor this year at University of Arkansas, so good for him. He has a paper on that, but basically builds the same premise. His paper looked at estimating the saturated model under a Bayesian framework, getting the covariance matrix, estimating our target, our CFA model under Bayesian framework, getting its model implied covariance matrix, and somehow comparing the distributions, the covariances between the two. So, posterior predictive model checking is used for almost everything, and generally speaking, fewer global fit statistics are available. However, you probably could think of a few of them. Like, for instance, leave one out, LOO. If you estimated the saturated model, calculated LOO, estimated the intended model, H0 model, estimated LOO, you could do a model comparison with it too. Okay. By the way, Learning Bayesian Statistics podcast, I was just on, taped it this week. It'll be out in a couple weeks, all right? So you see how much I have to say about Bayes. There it goes. And so, by the way, this is how much I give you the details. So you had a lot of stuff in Lisa's class, right? I don't want to reinvent that. Here's some model fit statistics that are in ML. Chi-square, root mean square error of approximation, CFI, comparative fit index, Tucker-Lewis fit index, standardized root mean squared residual. This, by the way, the standardized root mean squared residual is actually a raw data number, right? It's comparing your residual covariance matrix. It's looking at your residual covariance matrix, right? So these other ones are based on model comparisons. And here's a reference, a recent reference. Lisa actually provided in her last class as well, too. So I wanted to give you the theory without the actual, what it is. I hope I achieved that. How are we doing? Makes sense. All right, let's go to categorical, as Cass had foreshadowed. IRT models, we know the data aren't multivariate normal because we define them as Bernoulli. And there's no way you can get from Bernoulli to multivariate normal. Let's just be real. There's a normal approximation to binomial. Some of you get taught in intro stat. Do you remember that vaguely? And then you never use it again, but whatever. Anyway, I would say this. The target distribution is not multivariate normal. We're going to have to figure out what that is. Once you figure out what that is, it looks complicated to figure out what to do with it, but there's a few other competing instances where we actually can't assess fit to it well. So, second, I will also say that model fit in IRT has been underdeveloped research-wise. That doesn't mean it's not been studied, but if you look at the proliferation of model fit in CFA, particularly in the 1980s, and you look at what happened to IRT about the same time, not nearly as much, right? So, but in the last 15 years, there's been a lot of work on IRT model fit. All right, questions? Let's talk about that target distribution. Looks like I'm just going to lecture the whole day today. We'll get to that coding exercise next time, okay? All right. Target distribution IRT models. For binary item IRT models, the target distribution turns out is something called a multivariate Bernoulli distribution, or MVB, basically multiple Bernoulli distributions. Now remember, the Bernoulli distribution is the distribution of a single binary variable, right? It's like a binomial where we talk about successes, number of successes out of number of trials. Well, in this case, it's a binomial with one trial, and it's either a 0 when it didn't succeed or a 1. And usually we use this for correct, incorrect scoring of item responses, right? Now watch as I generalize what we did in the last one to this one. It's going to be a little bit, the process is the same, the distributions change, right? So the multivariate Bernoulli, turns out, has a probability for each permutation of a response pattern, for all the permutations. What do I mean by that? How many different ways are there of answering correctly or incorrectly 10 items on the 10 item test? 10 binary items. 2 to the 10th power. 1,024. Right? Multivariate Bernoulli says that each one of those possible permutations has a probability attached to it. That's our target model. Right? How many of you have ever estimated 1,024 probabilities? 1,024 probabilities. 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 1,024 prob Nobody. How many of you think any of those would be, but how many, let's do this, forget the probability, that's usually just count over n, right? If you have 1,000 people in a data set, that's pretty good. You don't have enough people to fill up a cell. I'm hinting at a problem that we're going to end up having. Right? So that's binary items. What if you have a polytomous item? Remember, a polytomous item, it doesn't have just have 2 categories. It may have 3 or 4 or 5. Right? Same thing. How many different permutations of response patterns do you have if you have 10 3-category items? It's 3 to the 10th power. I don't have that plugged in my head. One of you could probably calculate that pretty quick. Right? So that's a massive problem. Conceptually, what I want you to be thinking about is, I can't collect enough data to hit that target model. Right? So think of it this way. In CFA, we made the assumption that everything's continuous and everything's normal and we're all super happy. And that's all, we can almost always get model fit. Why is that? The set of parameters we have does not exponentially increase the number of parameters in our target model. What I mean by that, right? So think of it this way. If I have 5 binary items, let's see here, 2, 4, 8, 16, 32 response patterns. Sorry. Counting by exponents. If I had a 6th item, I now have 64. So I went from 32 things I had to estimate to 64. It's a lot, right? Think of the same thing for IRT, for CFA. If I have 5 items, well, I got 5 means, I got 5 variances, I have 5 choose 2 covariances, whatever that is. What's 5 2 choose 2? 4, 5, 10, right? So 20 parameters. If I go to a 6th item, I have 1 mean, I have 1 variance, and I have 5 covariances. So I only have 7 parameters. Right? So in CFA, adding 1 item brings about a non-exponential increase in the number of parameters for our saturated model. Whereas in a multivariate Bernoulli, adding 1 more item exponentially increases. In fact, doubles in binary items the number of parameters I had previous to that. That's a huge problem for model fit. So this, by the way, is multivariate Bernoulli distribution function. And this is where I was getting at. 30 items with 2 response categories has 1,073,741,824 response patterns. By the way, I'm trying to learn Spanish and German right now. And always the numbers throw me out. Well, check that. The whole language is just throwing me out. I'm bad at all, right? But numbers especially. That's a big number. It's 1 billion. How many of you have analyzed data from a 30-item test before? Almost everybody. Can you imagine a sampling design in which you had to go and collect enough data so that there were people in all those probabilities? You would need, I think we crossed 8 billion people in the world. You probably need that much because people aren't randomly assigning themselves to the probabilities that show up there. A lot, right? So, the larger the number of items, the more empty this probability distribution becomes, and this is our challenge. So, let's go back to, gosh darn it, what the heck was this? Lit tech error. Another note for a slide to fix. I'll have the slides fixed by next week, I promise. Slide 27. Okay. So, let's go back to the small example. 32, let's have 5-item assessment. 32 response permutations, right? And we collected 1,000 observations. So we have data in every cell, right? There is a way we could calculate for every possible response pattern what our model implied probability should be. I'll show you that in the next slide. It's not pretty. There's an integral that won't go away, but we could do it, okay? And if we did that, now we have if we multiply each probability by the sample size, we have a frequency observed, and a frequency expected. And this is where the back to the future part of this class happens, In your very first stats class, we used frequency observed and frequency expected, and we called it a chi-square. Right? Usually this is the Pearson chi-square. There's a lot of likelihood ratio-based version of the g-squared. Sometimes we talk about it. We use this. That's it. Does the model fit the data? Let's find the chi-square. Here's what we observed. Here's what we see with our model. That's great. But do you remember the caveat back in IntroStat? Some of you might be TAing IntroStat right now. I don't know if any of you are.
Off diagonals.
The counts or frequency in the cells, we have like minimum.
That's right.
values required.
I always heard 5. You need at least
Yes.
5. I don't know why 5. That doesn't make any sense. Like in all statistics, when you get that certain, I'm kind of suspicious. But yeah, turns out when you have 0 cells, another term for that is what we call a sparse matrix, where it's a bunch of zeros. The behavior of the chi-square gets crazy in that it no longer achieves what it chooses to do. The bigger the number of 0 cells, the more likely that this chi-square gets super, super large, such that you reject every model. And by super large, I mean like super big. If you choose the likelihood ratio version of it, the g-score, which I don't have on the slides, you've seen this, you may have seen it in other contexts before. I mention this here because g-squared has the opposite behavior. It gets super, super small, and you accept every model. So now you have 2 statistics that are asymptotically equivalent, meaning if sample size were infinite, they should give you the same number, completely divergent. One who gives you a p-value, one which gives you a p-value of 0, and one which gives you a p-value of 1. Or translating that into our model fit discussion, a p-value of 0 rejects that null hypothesis by saying your model doesn't fit. A p-value of 1 does not reject the null hypothesis, and so you can claim that it's plausible that your model fits the data. From the same statistic that's supposed to function the same. So what do? We just take the g-squared, then everything fits. All right, now we can introduce. Who was it that mentioned limited information or full information just a moment ago? Vladimir, you said full information? This is where I'm going to introduce it in model fit. We're going to have a similar discussion about it in estimation in 2 weeks. But in model fit, limited information. The full information is the entire response pattern. That probability that goes with the entire response pattern is called full information model fit. And why that's the case is I will show you in just a slide that for the model implied version of what this model is, we're using every data point to come up with every item. The alternative to full information is limited information, which means we don't use every data point. All right. Before I get to limited information, there's one more thing I wanted to mention. In the CFA model, we didn't have this exponential increase, right, of number of target model parameters whenever we add an observed item. And that's because in a multivariate normal distribution, there are only 2 sets of parameters, 2 matrices, a mean and a covariance. What's the third order? Sometimes we call these the first and second order moments, central moments. Right? You ever heard that term before? The third moment around the mean is sometimes called what? Skewness. There's no parameter for skewness in a multivariate normal. It's actually set to 0. Right? There's nowhere to derive it. We can't get it. We can go and estimate a sample estimate of what a skewness might be. But the multivariate normal distribution itself that we're implying with the data doesn't have it. That third order moment, first and second order moment and third order moment, are sort of what we're doing in limited information. In limited information, we could say, yeah, there's that full response pattern, this multivariate Bernoulli thing that has all these parameters, all these probabilities, right? But what limited information says, you know what, I'm not going to use all of these. nested within that whole response pattern are the other moments, the lower order moments of the data. First moment being the mean, effectively, it's a marginal proportion. Now we know, I mentioned just a second ago that most models fit the mean almost perfectly. Sort of useless information, but we can use it. Useless, but we can use it, that's bullshit. Spare nobody, including myself. The next level up, the covariance matrix. The analogous version of it. What a covariance is a quantity that describes how two variables are related. Right? We can calculate a covariance in binary data. Moreover, we could even get what usually it shows up as is a 2x2 contingency table. If we had a pair of binary items, how we describe their association is fully described entirely with the 2x2 table, right? Number of people who are 0 on one and 0 on the other. Number of, in all different permutations of 0 and 1, 4 squares, right? That's the limited information. Our goal is to take those tables and see if we fit those tables, the limited tables, not the full data themselves. And the reason for that is purely because there's not enough data in the world that we can collect to do model fit for most of these assessments. How we do it. So limited information means part of the data or summaries of the data. Full information means the ideal target, theoretically, and all the data. Questions? I can see the eyes like getting lower in everybody. I know it's a 3-hour class, and I wanted to break it up with coding, but I got a lot to say this week. I'm sorry. Maybe we'll do more coding next week. How's that sound? How about a bigger coding time? You just got to make it through 25 minutes, less than 25 minutes, okay? Okay. So, question? I'm watching the back, I'm watching the front, but that middle, I'm just kidding. And then there's the side. I don't even know about the side. Yeah.
Yes, I have one. If we're using the limited information method, why are we using this idea of moments instead of using, for example, a correlation matrix? This
Great
question.
question.
Polychoric correlation matrix.
Great question. And actually, when we get to the estimation of it, you will see we will actually do limited information fit when we do limited information estimation. But the answer to that is none of our model implies this. Nothing about our model implies it. There's no covariance implied anywhere in the thing. And so when we get to a limited information, what we're looking at is just the moment itself, contingency tables. We're a categorical-based model, we're going to work on the categorical-based contingency table. The other issue with correlation is there's no one correlation in categorical data that fully describes association of two variables. There are lots. There are lots of reasons for using either. Maybe you've heard of the phi coefficient. Help me out here. Correlations or associations in contingency tables. How many statistics does everybody know about that? You probably know a lot too. Phi coefficient, tetrachoric correlation, kappa, polychoric subversion of tetrachoric, right? You go on and on and on. There's a ton. And so the question then becomes which one, and then do we introduce a confound and fit? The more exact version of this from a limited information point of view is that contingency table.
Great. Thank you.
You're welcome. Thank you for asking. Okay, let's talk about the model implied conditional distribution now. This is our 2-parameter model, IRT model, for a binary item. And again, you can see I'm using the same linear predictor I had in CFA. Differences for this is that I'm predicting the probability of a 1, and I don't have error because error doesn't exist. It doesn't have a parameter. Error exists, but doesn't have a parameter. This distribution is Bernoulli. This is the bottom. Right, so this is going from the conditional model to which distribution it implies. The model implied conditional distribution, we then need to think about, that was one item. What about all the items? Well, again, in CFA, we had the assumption of conditional independence when the diagonal of the phi matrix, or psi matrix, the error matrix, was 0. In IRT, we just explicitly say we assume conditional independence. And the way we enact that is by saying items are independent. Remember, independent items. So I had a coin to flip, and I flipped heads. What's the probability of flipping two heads? 0.5 times 0.5, right? If it's a fair coin, by independence. So the flips are independent. So here we're multiplying item responses, meaning these are independent, conditional on a person's theta. So that gives us, right here, conditional on theta, what we expect. If we go and plug in all permutations of the data, and we know what a person's set of thetas are, we can get that expected probability for each possible response pattern for a person. Right? This is our roadmap for it. We have theta involved. We need to get theta out of the way. But I'm just trying. You can think about it. This is reasonable. It may take a lot of time, but you could do it, right? If you have 5 items, you want to calculate, answering 4 right and 1 wrong. The first 4 right, 1 wrong. You could do that. It's 4 products, right? Here is the problem. We got to get rid of theta. Theta screws everything up. Theta doesn't exist, so it shouldn't go and form our model fit. We've got to go and remove it, marginalize it. So here's our integral again. This, by the way, I don't have the joint distribution in here, but I have the conditional times the marginal. Evidently, I was thinking differently by the end of my slides, and you're probably thinking differently by the end of the lecture, so I know how you feel. Or you know how I feel, I don't know. And we just talked about why we can't use that. Instead, so this thing right here, this integral, we have to do this numerically if we want to solve for it. Meaning we have to approximate the integral using a series of quadrature points. I think you definitely heard about that in IRT class, maybe even in Lisa's class as well. Right, so you're sort of familiar with the idea of what we call numeric integration, which means we use a computer to do this integral, but the computer has to approximate it, right? So it's a fuzzy approximation, but it's a pretty good approximation. But this is where limited information model fit comes in. This is the article I sent you. This is one of the images. This is from page 176. This is the cool part of it. Here, on the right-hand side, is for a hypothetical 3 items. This is the 8 probabilities associated with each permutation of a response pattern. This is the target that we're after, right? But we can't build that target. We can only build moments that go into it. And this, I like this picture because it shows how certain versions of this matrix get nested within each other. Like all the moments are nested within this structure. This is full information on this side right here. If you go on the left-hand side, right over here, this partition vector right here are one-way first-order moments, or means, second-order moments, or two-way tables, and your third-order moment, three-way table. Right? And how you arrive at those, you can show through this. So for instance, if I wanted the mean of the first item, but I only gave myself this response, the probability of each response pattern, I needed to go and sum together the cases where the first item were 1. Here's 1, here's 2, here's 3, here's 4. Turns out that's where each one of those ones show up. So what that means is if I give you a vector of all the response patterns right here, I can go and get the mean of that response pattern by multiplying it by certain key values and get that out. Or another way of putting it, the way I look at this equation, is that all of the one-way moments, all the means, the first-order moments, are nested within the full information response pattern. Right? Now think of this, if I wanted the covariance between item 1 and 2, well, I need the place where item 1 and 2 are both 1. That's here. That's here. There's a corresponding 1 in each spot, and I can sum those together as well. All right? Likewise for each of those. So now,
Looks like a diagnostic problem.
there is a part of this that overlaps with the logic, certainly does. Grab the reading real quick here. This is where I'm folding in the reading into class, by the way. But here's what comes next. You notice that they took off the probability of 0, right? Because it sums to 1. All that whole vector sums to 1. So the probability of having like the 0 cell doesn't really need to be there. But then this M matrix right here, that's the thing in the middle. That's what this thing is right here. This matrix doesn't have to be the size it is right here. I don't have to have, for instance, the three-way moments to it, right? Right, if I removed this row down here, I would remove this element over here. But the matrix math still applies. And now I have effectively a vector that has the moments that I'm looking at. Right? Now I know discernibly, like theoretically, this is the theoretical proposition of going from the full information to the limited information, the lower order moments. Now it's up to me. I can calculate lower order moments pretty quickly. I still have the integral, but I have that. I can calculate expectations. And it's much more common that the two-way and one-way tables, right, the marginal and bivariate tables, will have people in all cells. So they're valid for a chi-square if I wanted to use it. So I can observe these in data really quickly. I can observe them. I can quickly calculate them, relatively speaking. Still has an integral, but still relatively quickly for all of my possible pairings of them. What the rest of this paper does is derives a sampling distribution for them to give you a test statistic. All right? Now that, by the way, that's some fun stuff right there. And I encourage you to, fun in certain ways. My eyes are rolling back this time of the afternoon. Let's just take their word for it. It's true. It's just showing you that certain observed versus expected frequencies, you can show that under certain conditions, there's an asymptotic distribution for them. You can estimate this quantity. So basically what that derives is now you can look at the quantities in your data and you can get a test statistic out of it. And there's a method, they end up showing, I think it's method of moments they use to go and derive a p-value for that. And now we have a test hypothesis for absolute model. This to me is awesome because we're not involving theta. If you look, I don't think it's as clear in this paper. Oh, the introduction to this paper is really good about this. The history of model fit and IRT is really kind of weird. And up until like the early 2000s, people were using theta in the model fit statistic in general. You may have seen it where you output people's thetas and you draw a ICC that you observed. The big problem with that is theta is not observed. Not only that, it's only probabilistic, but you conditioned on one value of to show model fit. Sort of it's the problem I had with validity being tautological. That is actually tautological. Plus, it's only fit to one data. So this is why this paper is really important. And I'm not going to go back to the slides now, but that's sort of the foundation for a lot of great model fit statistics in IRT that we should be using. There's a series of paper, Alberto Madeo Oliveras, who will be at our conference in October. He'll be here. He started this. I don't know why I have 2010 here. It should be 2006. He has a paper with Harry Joe, a statistician, who talks about it. That's where M2 comes from, by the way. The letter number 2 is the first and second order tables, the mean and covariance. You could have done a M3 or M4. And with that model fit statistic, you can derive a whole host of other model fit statistics like you did previously. So if you use the homework that I'm assigning you, I give you instructions on how to use M2. If you're using the MERT package in the preamble of the homework, there's instructions. There's an M2 function. It will run M2, but it'll also give you RMSEA, CFI, TLI, all the things that you see in previous places. Plus, from a limited information point of view, from a residual, if you have a bunch of two-way tables, you can also get a residual between items as well. But there are some drawbacks. Just because your data fit two-way tables doesn't necessarily mean, your model fits the two-way tables, doesn't necessarily mean your model fits your data. It just means we can't necessarily see if it doesn't. But I think generally speaking, fit to two-way tables is probably at least a good start. If you can make it fit two-way tables, I don't know how much different the other ones will be. It'll be harder. The other thing that's different about this, even though when you go and use M2 in your homework, you'll see an RMSEA, a CFI, a TLI. You'll see those. You'll connect those to what you see in CFA world. Their use is different. Like their scale is different. And it's not entirely clear what the values should be. There's a number of papers recently about whether we're using the wrong, like RMSEA should be less than 0.05 or 0.08 for roughly approximate fit. People kind of think that might be too lenient in these types of models because it's a different statistic altogether. Like it's essentially a different different scale, I want to say. It's derived from a different scale. Anyway, you can also get local misfit. Anyway, how are we doing? It's got 10 minutes left. It's been a long class, I can tell. Where did I fall off the rails for you? Or in terms of model fit, are you approximately with me? Like if I asked you tomorrow, you walk in the office, or I see you online, some of you I'm meeting with tomorrow, I don't have all my meeting. What's M2? What will you tell me? Fit to two-way tables and binary data. Bingo. By the way, you can imagine like the two-way tables may also have problems if you have polytomous items. So if you think of the case of like a 7-point Likert scale, like, you know, strongly disagree to strongly agree, neutral, whatever, right? The two-way table of that is not 2 by 2, it's 7 by 7, right? So there are all sorts, there's another all fascinating literature about how they try to approximate certain tables. There's, and in the MERT package is incorporated a number of these methods as well too. Okay, so limited information though, I mentioned this previously. In 2 weeks, we'll be talking about limited information estimation, because that's one of our ways around the estimation problems in multidimensional models. One of the problems we have in IRT models, this is not multidimensional, just IRT, categorical data in general is assessing model fit. But when we're going to go estimate a multidimensional IRT model, or categorical data with multidimensionality, we also have an estimation problem. Turns out there are limited information estimation methods. M+ defaults to them. Lavon only uses them. So if you used either of those, and their output will look very similar in terms of all the information statistics that you had. And I think one of you, maybe Cass it was, that talked about that, or I remember who asked that question, but talked about that. Same thing. So there are cases where you can see very similar, but those aren't M2 statistics. Those are based off of one connection to CFA. And that connection lies in the use of a probit link function. But I'll leave that for you to think about in the next few weeks. We often, normal ogive, probit, use those interchangeably. When you have that, you can start to do CFA things with the second order moments of your data. All right, last topic, Bayesian model fit, forget about it. Just don't do it. I'm just kidding. All of this is replicable in Bayes. All right, so I mentioned Zhihong. The paper he had, actually it was co-authored by Zhihong, and I'd be remiss to not mention another one of our graduates, or soon-to-be graduates, Katie Mintz, also was a co-author on that paper. Zhihong then also went and tried to establish this for M2 as well for his dissertation, and I'll have a link to that in just a moment too. But Bayesian basically is posterior predictive model checks. If you remember that from those of you who were in my Bayes class, but those of you who aren't, don't worry, you don't have to be. The idea is you take values, so in a Bayesian estimation, particularly a Markov chain, you're estimating, I should say MC estimation. You're estimating, you have sampled values from a posterior, so every iteration you have a series of parameters for all the parameters of your data. The posterior predictive model check takes all the parameters from each chain, assumes they're true, and generates data as if they were true. Right? So now you have a lot of simulated data sets. Right? PPMC then takes summaries of those data, marginal item statistics or bivariate statistics, and calculates what it looks like when you simulate data and what that same statistic looked like in your real data using like ML to get an estimate of it. And that is where we do model fit and Bayes. Don't have a whole lot there for it. But the other thing you can turn this into is a p-value. These are the references I really want to talk about. If you go and click on this, you should be able to get to each of these papers if you want to know more about Bayesian versions of these. And in Bayes, I really mean Markov chain Monte Carlo, because each of the methods that I've shown you before, if you're not doing Markov chain Monte Carlo, if you're using, we'd call like an optimization, if you're estimating the posterior mode instead of the MLE, most of what I showed you previous still applies. But PPMC is different. And finally, I know we have like 4 minutes left, so I'm flying here. Relative model fit. That was all absolute. Hooray, we're right there. There's that relative model fit. That's fairly benign, fairly easy, right? Generally speaking, if your models aren't nested, you use some type of information criteria. But again, you always remember, you need to check the absolute fit of each model before you use it. So if you have like 3 different models and you're only using AIC, that's not absolute fit. That is relative fit. So the AIC, DIC, there's a whole host of those as well. And in Bayes, we have the WAIC. We'll leave one out as well. Similar function to it. But I'm trying to give you the theory in this and not the practice, right? You've had the practice. And for those of you that took my Bayes class know this stuff. Those of you who've taken like factor analysis know the other things. I think you've had the practice before, but this is where that's coming from. Finally, if you do have nested models, the likelihood ratio test in ML works the best. It's uniformly most powerful, right? It's one of the properties of likelihood ratio, so long as they meet the regularity assumptions of the MLE, which most data do, unless you have some weird boundary issues and so forth. But most cases are fine. But yeah, all right, that's it. I know. You made it. How many of you are angry right now with me? Okay. We know here, one part of our mission in this college event is mental health, and I want to hear. No, I'm sorry. It's a long lecture, but I hope it gave you something you didn't see before, which is sort of where this goes. I'm going to leave you with some of these questions, though. Just to ponder. What if you had a bunch of Poisson distributed items? Count variables. How would you assess model fit? What if you had a bunch of CFA-like items for Likert items, and then you had a couple that were binary, and you used IRT with it in the same model? How would you assess model? There's no answers. I don't think we do anything, but I want you to think about that, because I've described this for you in very well-established but very narrow cases. Even though CFA seems like it runs the world of Likert data, and IRT is for binary, those are very narrow cases in a lot of what we do. But the need for assess model fit doesn't go away even if your item type changes. Okay? Alfonso, I know you did stuff with the beta model. How do you assess model fit? Ignore it. I'll go back. I'll give you one breadcrumb of where I go with it, right? This limited information idea, while you may not get a test statistic out of it, you can always get an approximation to it, right? So you can always generate a covariance that your model thinks an item should have and can compare that with real data. It's like a PPMC idea. You can always do that. At least it's better than nothing. So thank you for attending. Thank you for being here today. I appreciate it. Next week we'll have more data, more coding. I heard it was okay last time. I'll add more to next time, okay? Thank you.